Okay, so we have seen how a generalization of the exponential function to include complex variables uh, is possible in such a way as to leave it analytic. And it turns out that the exponential function so defined is actually analytic in the entire finite complex plane, and it's an entire function. Right? So we also said that for any complex number in the complex plane, it's possible to work out the inverse, right? So it's possible to find a corresponding complex number whose exponential will be a given complex number. If we go in that direction, so we encounter the logarithmic function, which is the subject matter for this lecture. So given an arbitrary complex number z, we wish to find a function f of z such that the exponential of this function or the value from this function e to the f of z must give back z, right? So if we write down z in polar form as r times e to the I theta and expand the function f of z itself as a real part and complex part, so u of x comma y plus I times v of x comma y, and so we immediately see that this is the same as asking e to the u times e to the iv, right? So this is a property of exponential of the complex number. It's like this: if you want to take the exponential of the sum of two complex numbers, it's the product of the exponentials of the two complex numbers. So you have e to the u times e to the iv must be equal to r times e to the I theta. So now you see that so this equation on the left hand side here, you have e to the u, which is exponential of a real number. So it must be, it's the usual exponential function. So there's the real part, and then e to the iv is where you get the complex part at all. So it's a phase which also appears on the right hand side. So whenever you're comparing two complex numbers, and if you want their equality, we know that the modulus of each of these complex numbers must necessarily be the same. So e to the u, which is the modulus which appears on the left hand side, must be equal to r. And also, if e to the iv is equal to e to the I theta, so we're saying that the arguments of this complex number are the same. There is some freedom, right? So as far as the relationship between v and theta is concerned, they don't have to be exactly the same, but v of x comma y can differ from theta by an integral multiple of pi. So this is a consequence of e to the I times an integral multiple of 2 pi being the same as you get back 1. So therefore you have this freedom to add any integer times 2 pi to theta. So while e to the u of x comma y must be equal to 0, v of x comma y is equal to theta plus 2n pi, where n can be any integer. So therefore, this function f of z, we can think of this as log of r. So log of r, where r is a positive real number, is of course a familiar concept, right? So it's the natural logarithm of a real positive number. And then, so there's an imaginary part. So this imaginary part is, there's some ambiguity around this, right? So it's theta plus 2n pi, where n can actually take infinitely many values. So in fact, this inverse function that we wish to define seems to have actually infinitely many values. For a given z, you can find infinitely many complex numbers such that e to the f of z equal to z. So you don't get just one answer, but in fact you get infinitely many of these. So this is something which we can define as the logarithmic function. So we write log of z as log z. So what is called a multi-valued function is log r plus I times theta times 2n pi, where n can take any of these values, 0, plus or minus 1, plus or minus 2, and so on. So it may be verified that e to the log z is equal to z as we desired. Of course, z cannot be allowed to be 0 because log of 0 is not defined, right? So you can take r to be very small and positive, but exactly at r equal to 0, this function has, a singularity. It's not defined at this point. So we seem to have managed to find the inverse of the exponential function, namely log z. It can be defined in this manner, right? It has this multi-valued nature, which makes it, somewhat tricky. So log of e to the z. So one aspect of this is, although it is, it's an inverse function, so e to the log z indeed is equal to z. But if you do, go in the other direction, if you try to find the log of e to the z, log of a complex number is not unique, right? The way we have defined it. So in fact, you could get z, but you also have many other answers around it, right? So which are all basically, z, but with plus some integral multiple of I times 2 pi, right? So you have an extra complex part, you have an extra imaginary part which comes in for free, right? So this is a little different from the kind of logarithm that we would, the properties of log of a real number that we are familiar with, of a real positive number that we are familiar with. So the moment you take the log of a complex number, there are these difficulties, all of which basically stem from the multi-valued nature of the log function. So it is convenient to define something called the principal value. So this is analogous to how we define the principal value of the argument function. So in fact, this multi-valued nature of log function can be traced to the multi-valued nature of the argument function, right? So this is how we got, this ambiguity in V comes from the fact that the argument of a complex number has there is this extra freedom, 2n pi freedom. That's where the extra freedom for the log function also comes in. So it's convenient to define the so-called principal value for the log function. And so when you refer to the principal value, we denote this as capital L og of z, right? So this is a single valued function, and so this refers to the so-called principal branch, right? So when you put n equal to 0, then this definition with n equal to 0 is called the principal value of the logarithmic function. So log of capital L og of z is equal to log of r plus I theta, right? Where now theta is just capital R of z, right? So this is also similar to how we can think of a small arg and a capital Arg, and where capital Arg is the principal value of the argument. And convention we are following here is to restrict this argument to lie between minus pi and plus pi, including plus pi, right? So in general, of course, it can take, it can range from any alpha to alpha plus 2 pi, right? So but I mean, it's convenient for us to choose this so-called branch to lie between minus pi and plus pi, as when we're thinking about the principal value. So the generalization of this log function is also carried out, keeping in mind these two requirements, right? So I mean, of course, we looked at it as an inverse of the exponential function, but indeed, so analyticity of this function is also, assured in a very large region. So we will discuss analyticity of this log function in a moment. But first of all, let us point out that this log function will indeed reduce to the usual logarithmic function if you have z equal to x greater than 0. Right? So you have a real positive number, it must get back to us the same logarithm that we already are familiar with. And if you're dealing with capital Log, it's just ln r as we know it, right? So I mean, even for real positive numbers, so there is this extra freedom associated with the log value. So there is a complex part which we usually ignore, right? So in fact, we are used to using just the ln of r as a numerical value. There is no complex part, there is no imaginary part that we associate with the log of a positive real number, right? But if you look at the small log, so the generalized notion of the log will actually be also multi-valued, for any complex number z, right? So this is something worth emphasizing. So the other property which is desirable is to ensure that this log function is analytic in as large a region as possible. So it turns out that when we are looking at this capital log of z, namely the principal value, we have restricted this capital arc to lie between minus pi and plus pi. So there is, one whole line of points which starts from the origin and goes all the way up to minus infinity along the negative real axis, which is somewhat problematic in the sense that this function log of z is not even continuous at that point, right? So this is something that cannot be avoided. So let's look at analyticity of this log of z. And so if you're on the negative real axis, there is a discontinuity. The reason is that this argument of z has a discontinuity as you cross the negative real axis. So this is our choice of what is called a branch that we are looking at, right? So your argument goes from minus pi to plus pi. So if you're slightly below the negative real axis, then the argument is going to be close to minus pi. But if you're slightly above the negative real axis, the argument is going to be plus pi. So as you cross this line, you're going to have a discontinuity, right? And therefore the log function capital log also has a discontinuity at on that line, and also at the origin, right? In the limit of small r becoming very small and going to 0, it becomes very large and negative, and you have a logarithmic singularity at that point. So all points from the origin all the way up to negative infinity are, there is discontinuity for the log function. It has a discontinuity. So there is no question of it having a derivative at that point, right? So we have seen that differentiability is a stronger condition than continuity. So if it is not even continuous, so there is no question of differentiability. And if it is not differentiable, there is no question of analyticity. But this log function is seen to be analytic everywhere other than this one, ray. It starts from the origin, goes all the way up to minus infinity, but everywhere else the log function is indeed analytic. As we can verify, the Cauchy-Riemann conditions will hold. So if you look at the real and imaginary parts of the log function, the principal value, you can write it as u of r comma theta is just log of r, and v of r comma theta is just theta. So for all r greater than 0 and minus pi less than theta less than pi, right? So now theta equal to pi is not included. Everywhere other than this line which goes from 0 to minus infinity, these four partial derivatives, dou u by dou r, dou v by dou r, dou u by dou theta, and dou v by dou theta exist, and they're given by these nice smooth functions. It's just 1 over r, 0, 0, and 1. So in fact they're extremely well behaved. So not only do these four partial derivatives exist in this region, but they're also continuous functions. So everything that we desire for these kinds of the real part and the imaginary part hold, and also the Cauchy-Riemann conditions are also satisfied, which we can immediately verify in polar coordinates. Dou u by dou r is the same as 1 over dou v by dou theta. Both of them are equal to 1 over r, which come from here, from these equations. Also 1 over r times dou u by dou theta is the same as 0, which is also the same as minus dou v by dou r. So both the Cauchy-Riemann conditions hold, and these nice properties that we demand for these functions u of r comma theta and v of r comma theta also hold in this entire region r greater than 0 and theta mod of theta less than pi. Therefore, the analyticity of the log function in this entire region is guaranteed, and so the derivative exists. The value of the derivative is something that we can immediately compute. We use the value of the derivative in polar coordinates. It's just e to the minus I theta times dou u by dou r plus I times dou v by dou r. But dou u by dou r and dou v by dou r are, dou v by dou r is just 0, dou u by dou r is 1 over r. So you have 1 over r times e to the I theta, which is the same as 1 over z, right? So the derivative of the log function is 1 over z, which also nicely generalizes from the corresponding derivative for the log function of a real variable. Right? So some for properties of the log function, let us quickly state them. So if you take any two complex numbers, multiply them and take the log of this product, then log of this product is the same as the sum of the logarithms of each of these complex numbers. So we must point out that each of these functions here, each of these quantities here, the left hand side there's one quantity, right hand side there are two quantities, so they're all multi-valued. So the way to interpret this statement is the way we interpreted a similar statement when we had arguments, right? So argument of z1 times z2 is equal to argument of z1 plus argument of z2, where you are using a small a, right? And so the way to interpret this is to say that if you take one value for this quantity and one value for this quantity, and if you add them together, you're going to get a value which is going to be one of the values of this quantity, right? So it's going to be a valid answer, no matter which value you take for here, which value you take for here. For sure the result is going to be a valid value that this function is going to take. So that's the way to interpret this. But when we take the principal value, this condition may not always hold. So one example is, suppose you take z1 equal to -1 and z2 equal to -1. So log of capital LOG of z1, the principal value is I pi, and principal value of log of z2 is also I pi, but log of z1 times z2 is is just +1, so which is log of 1, which is 0. So for this example we find that one of them will give you 0, but the other one will give you 2 pi I. So indeed this property does not necessarily hold if you have complex, if you're working with the principal value. But I mean, the more general logarithm function indeed has this property. The logarithm of the ratio of two complex numbers also has a similar result, right? So you can think of 1 over z2 as another complex number, and then basically it's really the same rule. Log of z1 over z2 is equal to log z1 minus log z2. If z is some non-zero complex number and n is an integer, then z to the n is going to be e to the n times log z, right? So this is also something which straightforwardly follows from the definition of the log function. And so if n were not an integer but 1 over an integer, then so you're looking at the nth roots of a complex number, z to the 1 over n. So here, although log z has, there is some ambiguity about what its value is, because you have all this many complex numbers which this corresponds to. But when you take the exponential of n times log z, so it's going to be n times 2 pi I here, and therefore when you take the exponential, all of them are going to give you the same answer. It doesn't matter which value of log z you take, but as far as this equation is concerned, there is a unique value both on the right hand side and on the left hand side. But when you take the nth root of a complex number, so z to the 1 over n, now you have exponential of log z over n, and so now because you have this denominator n sitting here, if you have I times 2 pi k, so there are going to be n distinct values for this, right? So this is something that you can verify after after the nth value, then they start repeating, right? Because exponential, there is this denominator, and then if you add some integer multiple of 2 pi, I times 2 pi, so it's going to be exponential of such a quantity will just give you back 1 after a point. So there are exactly n distinct values for this function, and that is also reflected in this quantity on the right hand side. All right, so although log z itself can give you infinitely many different values, whereas the nth roots of complex number are exactly n. As we have already seen, we worked out the nth roots of unity, and they all sit on the circle, and they are all equidistant from each other on the circle, and so they correspond to different phases, right? So I mean, it's exactly like that. And when you have some other complex number, you take its magnitude and pull out the magnitude, and then you're really working with the nth roots of unity. Okay, so in this lecture we have introduced the log function, and we have also talked about how the log function is in general a multi-valued function, and how we can consider the principal value of it. And we have also seen how the log function is analytic everywhere except, in a line which starts from the origin and goes all the way up to minus infinity. Okay, that's all for this lecture. Thank you.